Okay, so the rate equation for conduction is Fourier's law. So here's our ODE for energy. I want to turn this into something related to temperature. So here's Fourier's law, right? Fourier's law says that the rate of conduction heat transfer in the radial direction is minus K times the area. The area in the radial direction is 2 pi RL times dt dr. So I'll plug that into here, and I get this equation here. I'll just divide through by everything that's constant in the highest order derivative. So here's the highest order derivative. I'm going to divide through by minus K 2 pi, not R, because R is not a constant, and L, right? So I divide both sides through by minus 2K pi L, and I get this ODE right here. So here's my ODE for temperature. It's a second order ODE. It's not homogeneous, but it has the very desirable characteristic of being separable, which means that I can integrate both sides separately, right? When you have that kind of an ODE, it's generally pretty easy to solve it. I'll just bring this dr right here. So let's do this. Oops. I'll just bring this dr right here over to the other side. So I have d of r times dt dr, and then on this side I have minus r g dot triple prime over k times dr. We'll integrate both sides, and the way that I know that this is a separable differential equation is basically that I can integrate both sides, right? There's nothing on either side that gives me any trouble. R is explicitly right here. These other quantities are not functions of r, right? They are constant. So this integral is doable. When we start moving into more complicated problems, you'll find that there are equations that we derive that aren't separable. And the way you figure that out is you try, and then you run into issues, right? So this one, no issues, that's good. So over here, I'm integrating an exact differential. So I just get r times dt dr. And then here I'm integrating basically r. So r squared over 2, that's what I get right here. And of course, I need a constant of integration, which is C1. And if I solve this for dt dr, then this is my solution for dt dr to within that constant of integration. So this is still a differential equation. I need to integrate one more time. So I bring this dr over to the other side again. I have dt on this side, and then all this stuff times dr. Integrate both sides, which I've done here, and I get t on the left side, and then this becomes minus g dot triple prime r squared over 2 times 2 is 4k. The integral of c1 over r is c1 times the log of r, and then another constant of integration c2. So this is my general solution right here. This solution solves this ODE no matter what value of C1 and C2 you use, right? So the next thing I got to do is come up with some boundary conditions. So boundary conditions are at the boundaries of our computational domain. If you think about it, this function is valid between r equals 0 and the outer radius of the bale, right? So r bale. So I need a boundary condition at r equals 0 at the center of the bale, and I need a boundary condition at the outer edge of the bale, right? So at r equals r bale. So let's start with the one at the center of the bale. At neither of those two locations do I know the temperature, right? It's not like the problem we did before where the temperature at the boundary was given. That's a very easy boundary condition. Then you just plug that into your general equation and you get an algebraic equation. In this case, I don't know the temperature at the center of the bale, and I don't know the temperature at the outer edge of the bale, right? If we go back and look at our problem, the center of the bale, that temperature is actually kind of what I'm interested in. This temperature out here is not specified. What is specified is the air temperature out here, right? But the temperature of the actual hay that sits right here isn't specified, right? So what I have to do then is I have to come back in and make sure that energy is balanced at those two boundaries. So at r equals 0, and at r equals r bale, I got to make sure that basically the rate of conduction is doing what it should be doing in order to interface with its surroundings appropriately, right? That's basically what we're doing right now. So let's come down here and start at R equals R0. If I do a little interface energy balance and an interface control volume at R equals R0, I get this control surface that's just this kind of dot, right? It's basically saying I'm gonna draw a little control surface around the material right at the center of the bale, and then take that control surface down to dr equals 0. So this is a pretty easy energy balance to do. In equals out plus stored. There's no in because there's no volume inside of here, right? There's only out, which is the rate of conduction heat transfer in the radial direction at R equals 0. And since nothing else is going on, that conduction heat transfer has to be equal to 0. It's basically saying, you're not generating energy at this infinitesimal hole or point at the center of the bale, so the conduction there has to be 0, right? So that's what I have right here at the center of the bale. That's my energy balance. Whatever I do with this general solution, it has to be consistent with that. That's the way to think about this. Is the only way I'm chosen to write C1 and C2 is if at the center of the bale I don't have any conduction. So I plug in my rate equation. Here's my rate equation for conduction. This is minus K times A times dt dr. Evaluated at R equals R0. R equals 0. That has to be equal to 0. I can divide through by K and 2 pi and L, and I'm left with R times dt dr. At R equals 0 has to be equal to 0. R at R equals 0 is 0, so this is basically saying 0 times dt dr at R equals 0 has to be equal to 0. And so this is going to be true no matter what dt dr is at R equals R0, as long as dt dr doesn't go to infinity. So basically the boundary condition is telling me that dt dr at R equals 0 has to be some finite value. Any finite value will do, but what it can't do is go to infinity, right? So that's the boundary condition I have to work with. So let's plug in our general solution up here into this statement and see what it says. So dt dr is this guy right here, right? So I'm going to plug this into here, and it's going to give me this, right? So here I plug in 0 here, and I get this first term goes to 0. I plug in 0 here, and I get the second term is C1 over 0. Well, this second term is going to become infinite, right? And I can't allow that. The boundary condition says that it has to be finite. It can't be infinite. So the only way I can keep this second term from becoming infinite is to set C1 equal to 0. So that first boundary condition basically says you can't allow C1 to be anything other than 0, or you're not going to balance energy at the center of your bale, right? So C1 is equal to 0, so I can cross off that term, and I can cross off that term, and my general solution just got a lot simpler. It only involves C2. All right, so I have another boundary condition I have to enforce, and that boundary condition is out here at R equals R bale, right? So the boundary is R equals R bale. The way that I do these interface energy balances is I put one control surface just infinitesimally to one side of that boundary and the other infinitesimally to the other side, right? So the control surface that's in the material, so in this case at R equals R bale sort of minus, right? One atom to the left of this or inboard of this, that's going to be experiencing conduction. And then the control surface that's on the other side, well, that's going to be experiencing whatever the boundary condition is that you've exposed your computational domain to. So for this particular problem, this Q dot out is related to conduction through this plastic and then convection to the surroundings, right? And my boundary condition says whatever the rate of conduction is right here at the outer edge of the bale, that's my in, had better be exactly equal to whatever is being conducted and then convected through the plastic and to the air. So that's my Q dot out. So this guy right here is my boundary condition. Whatever I do up here with this general equation, it better satisfy that boundary condition. All right, so next thing we do is just plug in terms and try to make that work, right? This is conduction. Conduction is always governed by Fourier's law. So here I'm going to have minus K times the area, which is 2 pi r times L times dt dr, and I'll evaluate this at R equals R bale. So that's this term here. And then this term here is, let's see, I take the temperature right here on the inner radius of the plastic, and then I move towards the surroundings, and I find that the first thing I have to do is conduct through the plastic, so that's one resistance, and then I have to convect to the surroundings, so that's another resistance. So this Q dot is equal to the temperature here, so the temperature at R equals R bale, minus the temperature of the surroundings, so T infinity, divided by the sum of those two resistances, right? I know how to deal with conduction through a cylindrical resistance. I looked at that last time, or maybe 2 times ago. This is my equation for that. It's the natural log of the outer radius divided by the inner radius, and then I have 2 pi times the conductivity of the plastic times L. This is our convection. That's 1 over the surface area times h bar. So 2 pi times this outer radius times L. That's the surface area times h bar. These are my resistances. And then the other thing I have to do is substitute my general equation in for this temperature gradient and this temperature, right? So I take this equation here and evaluate it at R equals R bale and plop it into here. I take this temperature equation here and evaluate it at R equals R bale and plop it into here. And I end up with this equation here, right? So this is my conduction term, and that has to be equal to T minus T infinity divided by the resistances that stand between this outer temperature and the surroundings. So this is one equation in my one remaining unknown for C2, and I guess I could do some algebra and solve it, or I think what I'm going to do is just plop it into E's and let E's solve for C2. So somewhere here, oops, I went too far. So somewhere here, I have my E's code. So let's look at my E's code. This upper part is again just taking the inputs and converting them to base SI units. And then what I have down here is the solution. So this is the conduction resistance of the plastic. This is convection to the surroundings. And then this equation right here is my boundary condition, right? It's my one equation in terms of C2. And if I solve, I find that C2 is that value right there. I can use this now to make a plot of temperature as a function of R, right? Basically, I just go back and take my general solution right here. Now that I know C2, I can just use that to make a plot. So that's what I did here. This is my general solution. I can plug in any value of R here. So I made a parametric table and made, I guess it was this plot right here. So this is temperature as a function of radial location. You know, it makes a lot of sense to me when I look at it, in the sense that there's a flat boundary. There's a zero. There's a finite temperature derivative here, which says that I'm going to have no conduction at the center. That makes sense. And then as I move along, the rate of conduction is getting bigger, which makes sense. And then here at the outer edge, I'm conducting energy into that outer edge, and this has to then be convected to the surroundings and also conducted through that plastic, right? Yeah, so I could answer, I guess, my question that I started with, which is my hay bale going to start on fire? It turns out, no, it's not, right? 120 degrees is not 170 degrees, so I'm, not in any danger here of starting on fire. I could make my hay bale bigger, and I would see this temperature get bigger, right? If I make my hay bale bigger, I have more hay that's generating thermal energy, so that's bad. And that thermal energy has a larger resistance between where it's being generated and the surroundings, so that's also bad. So you'll see that this actually goes up pretty quickly. So if I wanted to, I could comment out R bale up here and then make a parametric table in which I vary the radius of the bale and keep track of the temperature at the center. And that's what I did here. And yeah, it's not a linear increase. It actually goes up pretty quickly, right? And 170 degrees, I can't make my bale much bigger than 2 meters, according to this graph. If I wanted to know exactly how big I could make my bale, I would do something like this. I would just comment out the bale radius, and I would say T is equal to T fire, right, 170 degrees Fahrenheit, and I would let E's tell me that, the bell radius is 2.125 meters at the point where you would start on fire, right? So 5 feet was fine, 7 feet not so good, right? That's what that's saying.